set number 4, question number 10. We are asked to perform a hypothesis test based on the idea that the long-term average, the true mean, the population mean, whatever you want to say, is greater than or equal to magnitude 6. The first thing we need to do here is identify a null hypothesis. And in order to do that, we should answer the 3 questions that deal with null hypotheses. The first one being, what data are we considering? So we look at the data in the question. The question says we want the North Mackenzie Mountains. We can see there's the North Mackenzie Mountains. It does not include the entire data set. So you should not have included the Beaufort Sea or the Richardson Mountains or the South Mackenzie Mountains. It's just the North. The second question you ask yourself with a hypothesis test is, or the null hypothesis, is what statistic you should use. We are asked to talk about a mean, so that is the statistic we will use. And the third question about null hypotheses deal with the inequality. So what direction are we considering? And that gets into how many tails we're using, what direction our tails should be. So at this point, I'm actually going to draw out our curve, thinking it might help. That might be my best one yet. The value we're comparing is 6. So we're dealing with whether or not our long-term mean is greater than or equal to 6. So our language there says that we are interested in, what we actually want to test is a big number. That way, whether or not our magnitude is 6 or greater. So that is what we want to know. Our rejection region is going to follow that. That if our value is in here, we will reject it. It will be greater than or equal to 6. Conversely, if this is what we care about, if we will get our paper published, if we will make it into the news when our earthquake magnitudes are greater than or equal to 6, if we will reject our null hypothesis if it's greater than or equal to 6, then our null hypothesis has to be less than 6. Notice it's not less than or equal to 6 because the equal part is already taken care of in the part that we care about. It'd be greater than or equal to 6. So all we need is a less than. Also note that it doesn't really matter practically speaking, but it's good for. So here's our curve. If you were to leave it at this, that's probably okay. It would be better if you also identified, and put this in a different color, you also identified that there's going to be a cutoff here that delineates the rejection region from the do not reject region. Notice here, kind of going with the hypothesis part, we have a one-tailed, right-tailed test. So we're only interested in greater than or equal to. We don't care about it being less. Less is our null hypothesis. So we only have one critical value that'll delineate this one rejection region. We do not yet know what value that critical value has, so that's really our next step. And that gets into part C. I should say for part B, ultimately it would be nice if this curve gets fully populated. If you draw out the curve, you put in your long-term mean, your population mean, you draw a critical value line, a rejection region. It would be nice if you put an actual number in the critical value. So later on, when you come up with a t-score, you can also put a t-score on your plot. And you can compare the two and make sure you're getting the right answer. For now, though, we don't know what the t-score is. We don't know what the critical value is. So the next step is to calculate the critical value. There is only one, as said previously. The critical value in general is defined by the number of standard errors we have to move away from the mean in order to produce this amount of probability. And we have to specify that ahead of time. Here is, as always, our confidence level. And 1 minus the confidence level is our significance level. And all of that significance level is going to go into this area this time because it is a one-tailed test. So I think in this case it's a 95% confidence level. So 1 minus 0.95 is 0.05. So all of that 0.05 is going to go into here. This area in the curve is 5% of the curve. So we need to calculate the critical value. Given that we know how much this is, we need to know the distance. So given a probability, wanting the distance is a .inv kind of function in Excel. We're using the t distribution, so it's t.inv. It's not .2t because this is a one-tailed test, so it's just .inv. The way this particular Excel function works is we have to give it not the tail that we're interested in, but we have to give it the complement, the probability from negative infinity up to the critical value, and it will tell us what the critical value is up to that point. So we give it the complement. All of this curve is equal to 1 minus the 0.05 that we have here means all of this is equal to 0.95. So that's what we put in the Excel function. It's a t distribution, so we need degrees of freedom. Degrees of freedom, as always, for t distributions is the number of data minus 1. Remember that our data set is limited to the North Mackenzie Mountains. So we have 8 data points. So 8 minus 1 is 7 degrees of freedom. We plug that in, and we get a critical value equaling 1.89. So starting at the mean, we can move 1.89 standard errors away, and that will leave us 5% in the rejection region. Note, and I probably should have started with this, this is a distribution, again, of sample means, not sample observations. So we're talking about standard errors. So we have a critical value, and we know this is now 1.89. That value alone does not do us any good. We need to compare it to a t-score. Say, within this plot, where do our actual data fit? Where does our sample mean sit? We, of course, had to calculate our sample mean first. So we do that. And then we need to see where it goes. So our t-score tells us where our sample mean needs to go. Our t-score is the sample mean, 5.88, which we calculate from the data directly, minus the population mean, 6. This was given in the question. This is what we're testing. Divided by the standard error, because this is a distribution of means. That's why we calculated a sample mean to begin with. So when we do that, we see that our data has a t-score of minus 1.14, meaning starting at the mean, the population mean, we move 1.14 standard errors to the left. And so this is where our x bar sits. So from these two things, our sample mean, x bar, and our critical value, we can do our first run at determining whether or not we should reject or fail to reject the null hypothesis. We have x. X does not cross the critical value. It is not more extreme. In fact, our critical value was 1.89. We're at 1.14. So even if you chose the wrong direction, it would still not be as extreme as the critical value. But don't think about it that way. Think about whether or not your x mean actually crosses the critical value. Our x bar, our sample mean, is going in the wrong direction from our critical value, so it was never going to cross. So we will fail to reject the null hypothesis. Our sample mean is not in our rejection region. So that's the answer that we should be looking for all of our other ways of dealing with hypothesis tests. The next one being calculating a p-value. So what is the probability of seeing our result or something more extreme under the assumption of the null hypothesis? In that case, under the assumption that the population mean is equal to 6, or greater than or equal to 6. So we want to calculate a probability. In order to do that, we need a distance from the mean. So we're going to use one of our formulas that have a dist in it. We're still dealing with a t distribution, so we'll use a t.dist. And we're doing a right-tailed test, so we're going to use the .rt version. And that does matter. You do have to specify that. We're going to have to specify our distance in standard error units. And in this case, the negative sign does matter. So the pluses and minuses. The sign matters for a one-tailed test, does not for a two-tailed test. So we take the absolute value. For a one-tailed test, it does. So we need to make sure to specify that our mean, our sample mean, is to the left of the population mean. If we told it was on the right, we would get a much different value. It would account for this extra probability. So we keep the negative sign, tell Excel that our sample mean is on the left. That 1.14, again, is a distance, and that is the distance of our sample mean, of our data. It is not the distance of the critical value. The critical value doesn't care what our data are. That's irrelevant. It just depends on the probability. So the probability of seeing our result, the p-value, does depend on what our result is. It depends on x bar. So we need to give it the equivalent of the sample mean in standard error units, because that's what we calculate probability on. So the value of our sample mean in standard error units is our t-score. So our t-score is -1.4. So we plug, going the wrong direction. So we plug that into here. We still need degrees of freedom because we're doing things with a t distribution. So we plug that all into Excel, and it tells us a p-value of 0.854. 0.85 is much larger than 0.05. So again, we are going to fail to reject the null hypothesis. It means it is entirely possible to observe what we did, or something more extreme, off to the right, assuming the null hypothesis, and the value of the null hypothesis being 6 or greater than 6. So notice this is very large value, so we're over here, and that probability includes the value that we saw or something more extreme. So it's all of this part of the curve. We know that this is 50% of the curve, so our p-value had better be greater than 50. And in fact it is, it's 0.8. So we've done a kind of back of the envelope check that yes, our p-value that high is reasonable. Again, had to be at least greater than 0.5. So that's good, and it matches the same do not reject conclusion that we reached using the critical value. So that's good. The third part was the confidence interval, and as mentioned before, we can calculate a confidence interval on a one-sided test. However, the confidence interval calculation is two-sided. So even though we will get a value for the confidence interval, and it is a correct confidence try that again. It is a correct confidence interval. That interval cannot be used to reject or fail to reject the hypothesis. The confidence interval is two-sided. We are doing a one-sided test, so we cannot, again, reject or fail to reject the null hypothesis, but we can still calculate the actual interval. And we do that by taking the sample mean, x bar, plus or minus, that should be a plus, or minus the critical value times the standard error. At this point, we have all of those numbers, so we can just plug them directly in. The critical value, well, I say we have the values. We don't actually. We calculated a critical value, but this critical value was one-sided. Our critical value for the confidence interval must be two-sided, because confidence intervals are always two-sided. So in this case, we actually have to calculate a new critical value for a one-sided test. And we use a different Excel function for that, the same ones that we've used before, but t.inv.2t to do a two-tailed test for the confidence interval. So we get that value instead, and ends up being 2.36. So we plug that in. The standard error came out of our data divided by the square root of n, or the standard deviation of the data divided by square root of n. So we get those, do a little bit of math, and we get a confidence interval that is from 5.62 as the lower bound down here, and it is symmetrical, and we have an upper bound up here of 6.13. So that is the range around x bar. Remember, our sample mean is what splits the middle of the confidence interval. And it doesn't really matter where the population mean, 6.0, falls into this, because we were doing a one-sided test. So we cannot use the confidence interval to do that sort of check.